Okay, so welcome back to the Applied Quantum Mechanics class after the Chinese New Year break. Let's recap what we have done so far in atomic physics. Basically, we assume that you have learned the basic solutions of the hydrogen atom problem using the Schrodinger equation. So we took that as the unperturbed problem. Then we started off with adding a magnetic field. And then we discussed that when we ignore spin, because all the orbital angular momentum are of quantum number 0, 1, 2, 3 for S, P, D, F states, even if you apply a magnetic field, you only remove the degeneracy behind the Z component of the orbital angular momentum. Thereby, you will expect to see this degeneracy split. For example, P state will become 3 different states, and then D states will become 5 different states. If we apply something called the selection rules that govern what are the delta M L allowed, then we found that at this level, we expect one spectral line to be split into 3 spectral lines in the presence of a magnetic field. That is the Zeeman effect, and this particular prediction, one line becomes 3 lines, is called the normal Zeeman effect. But when we look into data, we found that this normal Zeeman effect is not normally observed. More often than not, one spectral line will split into even number of lines, sometimes 4, 6, or even, as you will see today very often, even hydrogen, you will see 10 lines. One line becomes 10 lines. That required us to go further. So the first thing we ignored in the normal Zeeman effect discussion was spin. So we reviewed something about the spin orbital, spin angular momentum, and the associated spin magnetic dipole moment. Then we prepared ourselves with the general properties of angular momentum in quantum mechanics. So we proved that using the operator commutation relation properties, what are the required form for anything that we call angular momentum, what are the required forms of the magnitude square and the Z component. And then we realized that the orbital angular momentum is a special case that takes on integer number for the quantum number, and spin, electron spin half, is another special case that takes on S equals half. Thereby, you will have the Z component taking on 2 possible values only. Then we learned how to add 2 angular momenta, in particular, how orbital add into an electron spin half. So we have this notion about after adding them, we have J and Mj to label the states. If we don't have any further effects into the Hamiltonian, either you use the orbital L, quantum number L and spin, ML, MS to label the state, or you use JMJ, they are equivalent. Not this one is better than that, okay, because they are just as good. But last time we discussed spin orbit interaction effect. First, we derived the essential part of the spin orbit interaction term. And then we realized that with S dot L in the Hamiltonian, we better use JMJ. for the labeling of the states, because using that, it is very easy to apply perturbation theory. First order perturbation theory immediately will classify different J values into different energies. So we can explain the fine structure. Namely, we saw in data from spectroscopy that n equals 2 to n equals 1 is not only one line. They're split into very accurate data. The n equals 2 will have 3 different levels. But if we do what as far as we can with the spin-orbit interaction relativistic effect, we could explain a large part of it. N equals 2, there will be 2 different levels. That is the fine structure. The remaining little part is beyond our ability or scope of our course. That little part is called Lamb shift, a very famous part that Nobel Prizes were awarded, and also that had led to the formulation and success of quantum electrodynamics. That is part of quantum field theory. So with this preparation, we are now back to the beginning. We want to apply a magnetic field again to a hydrogen atom. But now we know that inside the atom, there is spin-orbit interaction. So we have a bigger Hamiltonian. The Coulomb, the part that you solved last term, the spin orbit, and also the effect of an external magnetic field that we call the Zeeman term. So we have a big Hamiltonian, and then we will exercise whatever we have in our toolbox perturbation theory to understand what will happen. So that is the first part of today's class. Okay, so you should see this Zeeman effect. So this part is about revisiting the Zeeman effect. Namely, again, we apply an external field. But now, better than before, we know that there is something else always exists inside the atom. That is the spin-orbit interaction term. In addition to that, we now have an external B field. Immediately, we know that there will be 2 additional terms in the Hamiltonian. The external B field will interact with the orbital magnetic dipole moment. That is due to L of the electron. And also, it will interact with the spin magnetic dipole moment due to the spin half of the electron. Remember, the magnitude, okay, of this is just a constant, because spin of an electron is always that boring half, okay? But there's a G factor equals 2 there. So let's put all the things together. The big Hamiltonian of this problem becomes the kinetic energy term plus the Coulomb potential due to the nucleus. So that is the part that you solved. That is our solved or unperturbed part. Then we learned that there is a spin-orbit interaction term. There's always there. Sometimes it is very weak, but if the atom is bigger, it will be more important, okay? And then there is now a Zeeman term. The Zeeman term takes on this form. We have a term that is L dot into the external field that comes from the orbital magnetic dipole moment interacting with the field. And there is another term that comes from the spin magnetic dipole moment interacting with the field. The difference is that there is a G factor, G equals 2, a very good approximation, although it is 2.0 something to 13 digits, but we will take it as 2 in our course. Because the G factor is different for spin and orbital angular momentum, so we will have an extra 2 here, and that matters, we will see, okay? So at this point, I would like you to understand, when we apply an external magnetic field, now we have this Zeeman term in the Hamiltonian. In fact, there are other relativistic correction terms, as we discussed, and also the TA showed you how to do it in the sample questions, but we will ignore this complication in this discussion with the external field, okay? So this is the problem we will solve. Last time before the break, we mentioned how we should handle such a problem. Now we have 2 additional terms, spin orbit and Zeeman. Which one is more important? It depends on the situation. If you have a strong field, you have a big magnet, then the Zeeman term may be more important, stronger than the spin orbit interaction term, because there is an internal field, right? The internal field is about 7.7 Tesla. We show you an example. So if you have a magnet with 3 Tesla field, then this external Zeeman effect will be more important than the spin orbit term. However, if you have a very ordinary magnet, something of the order of 0.something Tesla, then the spin orbit term will be more important. So depending on which situation you are in, you do the more important term more carefully, meaning more rigorously, hopefully exactly, and then after that, do the secondary term, the weaker term, using perturbation. So that is the big picture and the key idea, okay? Therefore, we will split the discussion into 2 cases. Strong field, in which the Zeeman term is more important, we will do this part more carefully and then handle this by perturbation. And the weak field case, where we should do the spin orbit first and then do this Zeeman as a perturbation, okay? Just to remind you, for the weak field case, this has been done. The spin orbit part, we did it, right? JMJ can conquer this part, and then we have to handle the Zeeman term in a perturbative way, okay? So we are prepared for this problem. So the moral of the story is, if you have many things to do, do the most important thing first. Well, that is common sense, and we are doing it in quantum physics. So now let's start. Strong field, Zeeman term dominating, okay? Let's look at what we know. If we ignore both terms, this is our solution. That's what you learned last term about the hydrogen atom or any central force problems. So we have this solution, spherically symmetrical. So we have this YLM theta phi that give us 2 quantum number, orbital angular momentum, and the Z component. Then we have this Pauli spin, this 4th quantum number so-called. This is plus minus half ms. I put in an S just to complete the list, but this S is always half for the electron. So very often it is skipped, but we better keep it for completion. And for hydrogen, it's a very special case. The energy only depends on the quantum number n. It is accidental. For central force, it is related to N and L. So that is the common ground we start our journey. And now we want to handle the Zeeman term first. Okay, so Zeeman term. The Zeeman term is this thing. Due to orbital and spin magnetic dipole moment interacting with the external field. You apply an external field, I call that particular direction Z. Therefore, we pick up the Z component of L and S. Okay, so that is rigorous, no approximation. The applied field will select a particular direction that we could call it Z. But we realize immediately that we have a very happy occasion here. This unperturbed state of the atom happens to be simultaneous eigenstate of LZ, because that will be MLH bar. That is what you did when solving the spherically symmetrical potential. The YLM theta phi part, that is the phi variable here, okay? So immediately we see that applying a field will remove the degeneracy hidden behind ML. And that is what we discussed previously in the chapter when we ignore spin. Now with spin, we only have an additional term with a G factor 2. So we have 2 SEZ, but that's nice. If the state is up spin plus half, then immediately we know that this is also a simultaneous eigenstate of SEZ. You will pick up MSH bar when this state is being operated by this operator. Okay, so this will look for what is the value of MS and return this eigenvalue. So simply put, we don't need to do anything more. If we use this labeling of the state of the hydrogen atom, the Zeeman term can be done in one line. The eigenvalue will be ML plus 2MS times this Bohr magneton and the external field strength. Okay, so we are done in one line in handling the Zeeman term in strong field. But you should realize that we have made a choice here. We have made a choice of labeling the unperturbed state in this way instead of JMJ, because using JMJ will be inconvenient to handle this Zeeman term. Okay, or we can revert the statement. The Zeeman term requires us to make this choice because that is the more important term. When we handle it, we are forced to make the labeling of L, ML, and SMS. Okay, so conclusion. The more important part in strong field can be handled easily and exactly without any effort, because this labeling of the state automatically gives us the eigenvalue. Okay, so now minus 13.6 divided by n squared splits. Okay, depending on the value of L, you have different ML values, and spin is plus minus half. So we are done. Okay, so this page just reminds you of the notation. So we have made this choice, and then when we operate SEZ onto it, then we'll pick up the plus minus half H bar Z component of spin. Next, we handle the less important part, spin-orbit interaction. Recall, the spin-orbit interaction is of this form, where this p-factor function of R is a big chunk of terms. But basically, it is related to the derivative of the Coulomb potential with respect to R, the radial distance, okay? But in our discussion, we will not do the p-factor part very carefully. We aim at showing what happens. What is the splitting that is resulting from S dot L? Okay, so that is the point. So first order perturbation is the first thing to try, right? So the story now at this point is that we solve this exactly. The unperturbed states are this kind of atomic states. Now we have an extra term. So what? Try first order perturbation theory, meaning the shift in energy will be given by atomic states in this label with the spin orbit term in between. So it's the expectation value of H prime. Okay, so this is the first order term. So follow me. Is that okay? Okay, so do you understand why I write down this term? Okay, and now suddenly, that's the punchline. Okay, that's why I pause and see whether you follow me. I go into the toolbox, I pick something. This is simple, I use it. Okay, get me? So now we need to evaluate this particular expectation value. All right. Now, because we are forced to use this labeling of the Z component of spin. So these are the eigen state of SEZ. Okay, just remind you that. Then we better stick to a Cartesian way to handle this thing, right? So S dot L means dot product of two vectors. Okay. Now, just focus on Sx, for example. You have a SEZ eigenstate, and you are looking for Sx expectation value. Okay? Now, just to remind you, you prepare a spin Z, SZ. You prepare that state to be an eigenstate, spin up. Then you fly this particle into a Stern-Gerlach experiment, or you put the magnet's orientation into Sx measurement. Then you will see two beams coming up. Okay, you will find equal number of this particle will have Sx being plus half and Sx being minus half. That is Stern-Gerlach experiment. Thereby, the expectation value, you try many times the experiments, you average over the experimental result, right? So 50% chance up, 50% chance down, the expectation value will be 0. Okay, do you follow this argument? Do you see why suddenly the next line I say Sx is 0? Okay, I'm using what you did last term. Okay, I read your notes, so I think you have that. All right. So similarly, we can argue that Sy term is also 0. Okay. In fact, if you don't use this, you could also try to evaluate Lx expectation value with Y Lm theta phi. Now that is Lz's eigenstate. You can do this, that is a derivative in between, and then you do this integral over theta phi. You can also get the zero. It doesn't matter. Both terms are zero, okay? But I argue one is zero, then it's zero, all right? So this term is also the same situation, the Stern-Gerlach experiment, you put it in the y direction, you fly SZ eigenstate into it, you will get two beams out, okay? Nice. The only surviving thing is this SZ LZ. But that's so easy, right? Because this choice of label already give you eigenstate of LZ and eigenstate of SZ. Recall, SZ will return MSH bar, LZ will return MLH bar, because the state on this side is an eigenstate of LZ SZ. How nice. So suddenly, all in all, this L dot S term will give you ML MS H bar square. We are done, okay? But don't be too happy. There is a R integral to do. Recall this is a function of R. This wave function has a radial part. R and L, which is a function of R, the radial function, okay? So you can look up what is the hydrogen state. I'm using that argument. There is a question posted by Ling. So I'm using that, but the first thing, MS is the plus half, means spin up in the Z direction. So if you operate SZ onto plus half H bar, you will get plus half H bar. Okay, do you get that? Okay, so that's why this is not zero. And this gives us MSH bar. Get me? The other one gives us ML another H bar. That's why we have a square. Okay? But this is the number in front. There is indeed a rather clumsy integral that we have to do. We have to look up the hydrogen atom's radial thing. Wow, the big chunk here. Okay, H bar over some M square, you know, C to the cube, and then 1 over R dV dr. We have derived it. And then R squared dr. Nonetheless, we can write it down and ask someone to do it, okay? But that's why I don't care about what is the resulting term here. I just use a symbol, an expectation value that has to do with the radial part. Then this is the key result. Let me summarize. We use this state to handle the Zeeman term exactly because it's more important for strong field. Then we use first order perturbation theory to handle this spin orbit term. Okay, it turns out that we can do that, okay? And then this is the result, apart from an integral to be done. So these 2 pages are just the argument that I made, okay? So it's the same thing. So let me conclude this treatment. Last term, you got that. Now with Zeeman term including spin, we have orbital and spin effect. This is the strong field result treat it exactly. Then the spin orbit term is secondary, weaker. First order perturbation, we have this prefactor with a radial integral that can be done. Okay, so we are done with the problem, strong field. Okay, so what happened? Let me show you for a P state. 2P, for example. Okay, so P states. Remember, P states means L equals 1. ML is 1, 0, minus 1. Spin plus minus half means up and down. Thereby, there are altogether 6 P state. That's what you learn in high school. Periodic table. Okay, when you go to that row, you have 6 P states. Now, we use this label, MS, ML. Now, let's prepare for ourselves. We need this combination. Okay, so the 6 states can be labeled this way, pairing up the ML and MS. All right, so this is Y11 times spin up. Okay, that means that. So we have this. These are the 6 states using ML, MS labeling. Now we prepare ourselves. We need this particular combination, ML plus 2 MS. It's easy. You just calculate what is this, okay? And then I list them out here. Just to call your attention to that there are 2 different states in this labeling give us the same value of ML plus 2 MS. 0, 0 here for 2 different cases. Okay. And then we have this combination, product. Let's prepare ourselves for that. 1 times half is half and so on. So I list them here. Okay, just to prepare. Now, let's get to work. So we have this to start with. And now what happened if we include this term and that term? That looks complicated, but not quite, okay? So for the moment, let's take these 2 terms into account. Forget about the last term, because this is the more important part, right? So this is what we start up with no Zeeman term. There are 6 states degenerate. These are the ML, MS take on different values. Okay, follow me up to here. Now we have this Zeeman term. See the highlighted part? All right. But we prepared ourselves for this combination. There are 5 different values, not 6 different values, okay? 2 of them are the same. And then that means 2 states are not shifted at all because the combination is 0. So I have 2 states here, not shift, remain on this value. Okay, and then I have a state that is 1 times whatever in front, okay, and twice, -1 and -2. So they are equally spaced. Okay, so do you follow me? This is mu B external field, okay? I have 1 up here, another further high up, 1 down, and another further down. Okay? Nonetheless, they are equally spaced, and this spacing depends on the spin strength, ball magneton, and your external field. All right? So it looks like what we learned before, but more complicated, you see, with spin. And the B field does not remove all the degeneracy. You see, there is one remained doubly degenerated. Okay, so altogether 6 states, no more, no less, but 5 different energies. Okay, follow me here. Is that okay? Okay. Now let's add in the spin orbit term. The spin orbit term is this thing. ML times MS h bar squared times an integral. Okay. After you integrate, it is just a number. All right. It will be something like 1 over ball radius cube or something like that. Okay. So let's look at it. We have, again, 5 different values. All right. So now let's do it. For the 2 that is not shift at all, now it shift down a little bit, but with the same amount because they are both -half for this combination. So they will be shifted a little bit down. Okay. And now for the one that is higher and the one that is lower, the shift will be 0. There will be no shift due to spin orbit effect. So this is the same, no shift, no shift. Similarly, for the highest one, it will be shifted up and shifted up, okay? What I call delta S spin orbit here is this fixed amount, okay? Now, let me summarize. 2p state start off with 6 states. You applied external field inside the atom, there is spin orbit. When your external field is strong, what happened is that this 6 state split into 5 different levels. That's the conclusion. Okay? Not trivial. Highly non-trivial, I would say. Okay, you may think, oh, 6 are split into 6, but suddenly the 6 states split into 5 different levels. Okay, follow me. In atomic physics context, you will find this discussion under the name of the Pershing-Beck effect. Okay, so what happened afterwards is that you can try to work it out for S state, D state, and then you will see the P goes into 5 states, and then D goes into more states, and then with the selection rule regarding the delta ML part, okay, and then all in all, suddenly the conclusion is 1 spectral line will only give us 3 spectral lines, no more. So again, this is just what we predicted in the normal Zeeman effect ignoring spin, although the atomic levels speaking is more complicated indeed. We can handle it, okay? So I just claim it that after you worked all this thing out, it's still odd number, 3 nines. So we still have something to do. We still have something to explain. Why we see 4 lines? Why do we see 6 lines? Okay, and that is the more interesting case, weak field case. All right. So now we switch gear. the spin orbit part is more important. We do it first. Then consider what happened if we turn on a small external magnetic field. We should do the spin orbit part first, but we did it last week. We know that if the spin orbit part is more important, then we should change the label of the state. We don't use what we did just a while ago, MLMS. Instead, we use JMJ. We handle the fine structure first. Using JMJ, recall, the result is that for an atomic state, say 2p, okay, and L, it will split into L minus half, L plus half for the J value, and they will take on different energies. That is the fine structure. We don't need an external field, okay? Now, on top of this, we apply a weak field. The question is what happened? This is the weak field Zeeman effect. So let's look at what the question is. It is rather complicated. The Zeeman term happens to be the external field dot into L plus 2s. This 2 comes from the G factor of spin being 2, which is different from the G factor of the orbital angular momentum, which is 1. Okay, so that is the difference. And that is a very bad 2. Okay. For the reason L plus S is J. If the 2 were not here, then we have L plus S. This is J, and the labeling using the J quantum number will be perfect. That will pick up JZ. Suddenly we know the answer with no effort, right? Because MJ is the eigenstate. However, life is not that simple, and nature gives us this G factor too. So the first thing you have to realize, there is some difficulty, all right? Nonetheless, we look into our toolbox and look up what to use. Of course, perturbation. And among the perturbation formulas, of course, the simplest one goes first. That's life, right? So we pick up first order perturbation theory first. All right? So we can write down an expression and then start thinking about what to do with it. So the Zeeman shift weak field should be, we use this labeling to handle the spin orbit effect. We will put that on two sides of the integral and then insert this term in the middle. So if we can do this integral, then we are done with first order perturbation treatment of the weak field effect. Okay, so follow me up to here. Okay. Okay. So now we are done with what we have in our hands, in our toolbox, okay? The next arguments is similar to what we did previously, okay, 15 minutes ago. I write down now, this is what we use, and then we start argue how to proceed. So this is what we have, and we use the two, first order perturbation, okay? And now the difficulty is something that we have to get through it or find a way out. That is how to do physics, right? Find a way out, okay? Don't just get stuck. So first, understand the difficulty. The difficulty, as I already mentioned, is this bad 2. Let's look at what it is. We have L plus 2S. That is to say, we have L plus S plus S. L plus S is good. It is J. We like this term. Okay? But then there is an extra S. So it is J plus S. So this thing is extra. That is to say, formally, this is not something, this term, okay, is not something that is parallel to J. It is J plus S, slightly in different direction. Okay, that's the problem. So come back here, we encounter something like J plus S. Okay, because L plus 1S is J, so we have J plus S. The first term, J, we love it, we keep it. The problem is how to handle the extra S. So let me introduce the idea before we take a break. Then we better find a way out, okay? We are going to do something more than first order perturbation. We will do an extra approximation, okay? The idea follows as this. It will be nice, we think, if we could simplify this term, although formally it's not something like this, but we want it to be this way, okay? So how can we get it? Can we approximate this total magnetic dipole moment due to spin and orbital angular momentum to be something approximate that is really parallel to J, okay? So we want to do it. And we don't mind if we have to tune this prefactor G so that we can get at such an approximation, okay? So the idea is as follows. If we can do it, that's our wish, okay? If we can do it, life will become very simple. The perturbation would become this. This is no longer the troublesome thing, but it is parallel to J. That is the Z direction. Then we pick up the JZ. We use the label that goes with JZ, that's nice. And therefore suddenly know the answer. This is MJH bar, and that is Bohr magneton, and then we are done, okay? So if we were approximating this, then suddenly we can do first order perturbation, okay? So when we approximate it like this, the answer is very simple. Bohr magneton external field, we pick up the MJ label, we split the degeneracy behind this MJ, okay? But all in all, there is an unknown number. The G factor we are willing to change to something else so as to make this approximation reasonable. So that is the G, okay? So that is the idea behind the approximation that we are going to make. We can make this approximation in one step. The idea is as follows. How about this? We take the projection of this extra s onto the direction of j. We ignore the other projection. That is the idea. Okay? Let me repeat. The original term is L plus 2s, which is j plus s. This part is good because it is already parallel to j. That is what we want. However, this part does not go along with j. It has its own direction. But we want to make an approximation that this whole thing more or less parallel to j. So how to do this approximation? Project this onto the j. Okay, that is the part that we want to take and ignore the other projections. So we have this idea already. We can do it in one line. We want to project s onto the direction of j. What is the component? This is the unit vector in the direction of j. So when I dot this into this unit vector, that is the component in that direction. And I need a vector that goes in the direction of j. This is the unit vector. Okay, so s dot here is the component of s in that direction. I give back the direction, the unit vector in j direction. Okay, follow me? So this is the projection. Okay, suddenly life becomes very simple. I have s dot j, I have a j square, then I have a j. When I see s dot j, I know what to do because we learned some trick in spin orbit interaction. Remember that j is L plus s, thereby L is s minus j, j minus s. I do L square, I will pick up the cross term. So s dot j can be written as L square, s square, j square combination divided by 2. Okay, so this projection can be written as such. Okay, put together the two things. J plus s, which is not in the direction of j, can be approximately bring into the direction of j by keeping just the component of j along the the component of s along j. And the result is a factor in front, j. This is a further approximation, okay? That will become our g factor, the g that we are willing to change, okay? So I will pause for a break, and after that, we will see suddenly with this idea of finding a way out, we can achieve a lot of things. In particular, explain why we have this anomalous Zeeman effect in which we will see 4 lines, 6 lines, okay? Even number of lines. So let's take a break and then we will resume at 1/2 past.